we're in the gas chromatography analytical lab. So all these instruments in here are used as gas chromatographs. This separates, detects and quantifies different compounds within a mixture. So here we'll inject liquid or gas samples and they would be injected into the system. We're using a flow of carrier gas. These will be sensed by a detector at the end, and this we can look at on screen and look at peak area and compound concentrations. This technique is important in environmental testing for looking at environmental contaminants at low concentrations and volatiles in samples. We support projects within environment, agri-food and water analysis, as well as soil analysis.
This system here is an automated thermal desorption, gas chromatography, time of flight mass spectrometer. It works by taking volatiles out of any sort of system where you can have volatiles. So we can take, for instance, a sample from somebody from their breathing space. So this is a passive way of getting a sample onto what we call a thermal desorption tube. It's a stainless steel tube and it has absorbent material inside the centre of it. And when we take the caps off the end, then a sample of whatever volatiles we're looking for can then be introduced into the TD tube. There are different ways of doing this. So we can do it by the passive method, and this is a useful way for people working in factories and if they're breathing in paint fumes or an automobile factory where there's lots of chemicals in the environment. Other ways of introducing samples onto the TD tube are by pump sample. Using a pump, for instance, like this, we can actually take a measured volume of the air that's coming out of a sample. In this bag, I've got some apples. We do a lot of post-harvest technology on fruit and vegetables. So this is a sample of apples. We put them into these bags and then we fill the bag up with zero grade air, with no volatiles, with no other hydrocarbons in the air. And we can leave that running for about 5 minutes. After 5 minutes, when we've carried it over at 100 mils a minute, then we have a volume of 500 mils inside the tube. Thermal desorption techniques are very good because they don't use any solvent extraction for the process. Once we've got the sample onto the tube, then we put it into the system. We have to change the caps to these new caps called diff-lock caps. Then it goes into the system, into these little trays. So what happens next is the sample then gets heated up and goes onto a cold trap. This gets focused on the cold trap and then it travels through with a flow of helium gas into the GC. And this column will then separate out all of the components from the thermal desorption tube. This system has a time of flight mass spectrometer and it ionises the samples, compounds coming out at the end, and then we can identify all of the different compounds that we're finding. Then you look at your chromatogram and you can see different peaks on here which actually show what the compounds of interest are that we're looking for. So if we focus in on one or two of these compounds, so for instance that peak there, we can identify now what it is. There's software in the system that enables us to identify them by looking at their mass ions. And then by using a comparison from a library, it will help us to find out what the unknown compound is from a list in the library that it compares with. So we can do a pretty positive analysis of what that compound is. In post-harvest technology, we want to make sure that we're getting fresh fruit and vegetables that have been stored for any length of time. So we're looking for particular compounds that might be oxidizing compounds that will degrade the fruit. We're trying to find new ways of preserving fruit for longer, so then we can actually find out if the quality is maintained for longer. We also do work on looking at biomarkers from clinical samples. So for instance, we've done projects on looking at fecal samples, for instance, and finding out what compounds are in them to identify inflammatory gut diseases, looking for biomarkers that then could indicate disease. I've been doing this work for about 11 years now, and I still know only the tip of the iceberg. So for a master's student or a PhD student that wants to come and work here, they will get to know a portion of how these things work, and they'll be able to do it for their analysis, so they can get something semi-quantitatively or fully quantitatively from some of their project work that they need to do. Last year we did a project for McDonald's, looking at volatiles coming out of the hot fat containers. So the students went away to McDonald's and collected samples on these TD tubes. This is another really good thing about this system, is that you can sample remotely. So the master students took their samples, brought them back again, and we put them on the machine, got the data for them, and then they took that data away and did all their statistical analysis for it. This system actually has got a huge range of applications. It can be used for forensic analysis, it can be used for pesticide analysis. There's a lot of atmospheric measurements that go on with this system. Several years ago there was a project on cabin air quality. This system is also very good because we don't have to solvent extract the samples before we introduce them into the system. So it's a much cleaner and an efficient way of preparing the samples. Also, the samples aren't actually affected by chemical changes or heat changes. This system is fairly specialised. As far as I'm aware, when this was installed, there were only about 6 other systems in the country. So it is fairly unique.
So here we have 2 Agilent GC systems. One is installed with a FID, which is a flame ionisation detector, and the other is installed with an ECD, which is an electron capture detector. Here at Cranfield, we use the GC FID predominantly for lipid analysis. So we look at PLFAs in soil samples. The ECD is mainly used for disinfection byproduct analysis. So it's used to look at halogenated organic compounds in drinking water or treated water. The GC FID is mainly used for PLFA analysis of soil samples. So by looking at a PLFA fingerprint, you can get an idea of the microbial community within the soil sample. And this is useful in the farming industry and agricultural industry. The GC ECD is mainly used for water analysis. So when you disinfect or chlorinate water, you get harmful byproducts. So this is important in the water industry, particularly the drinking water industry, to make our drinking water healthy for consumption. These pieces of equipment are quite widely used in various sectors and various universities or industries. So once you get to use it here at Cranfield, this could be very useful elsewhere. You'll do a sample extraction at first and you'll end up with a solvent sample in a vial like this. This will be loaded onto the autosampler. The autosampler will automatically inject a sample into the inlet where it is vaporized. Inside the GC here is a capillary column. This is a thin and long column which has a stationary phase that coats the inside of the column. When the sample is injected and carried along this column using a carrier gas, the compounds in the sample will interact and elute from this column at different speeds. This will then be detected by the detector at the end in the form of a peak, which we will see on the computer screen. This will be used by MSc students in their water courses, so looking at water treatment or water processes, they may use this equipment to look at the byproducts produced.